Hello all, welcome to the video for section 2.2, the inverse of a matrix. So we know that 2 times 2 inverse is just the same thing as 2 times a half, and that's equal to 1. And what we're looking for in the section, at the beginning of the section, at least, is an analog for matrices. So first we need to figure out what the number 1 should be, since it has a sort of unique position here. And recall that the matrix I, the n by n identity matrix, this is the matrix with ones on its diagonal and zeros elsewhere. It has this nice property that I times a is equal to a, and so is a times I. And this is the same property that 1 has with respect to multiplication of real numbers. And so the 1 here is going to be replaced by our I. We're going to look for some kind of equation like a matrix A times its inverse is equal to the identity matrix. And that sort of motivates this next definition. So an n by n matrix A is called invertible if there is some n by n matrix C with exactly that property, that A times C is equal to the identity matrix, and so is C times A. In this case, we call C the inverse of A, and we write that C is equal to A inverse, A with a superscript -1. Right, and this note here is just saying sometimes we call non-invertible or invertible things non-singular, or singular things non-invertible. So singular and invertible are opposite concepts. So let's look at our first example, and let's just multiply A and C together and verify that they're in fact inverses to each other. -7, -5, 3, 2. We know we can just take the dot product of the first row and the first column to get the respective entries for our product. So we've got 2 times -7 plus 5 times 3. That is -14 plus 15 is 1. We've got 2 times -5 plus 5 times 2. That's 0. We've got -3 times -7 plus 7 times 3. That's 0. And then finally, we've got -3 times -5 plus -7 times 2. So that's 15 minus 14 is 1. Okay, so that one checked out. I'll leave you to check that actually this is also true. That if you do it in the other order, you still get back the identity matrix. Okay. Oh. Brings us to this next little theorem. At least in the 2x2 case, there's a really quick way of checking if a matrix is invertible. So if our matrix A is this matrix A, B, C, D, if just as long as this number AD minus BC is non-zero, then somehow, we'll look at the details later, somehow A is invertible, and better, we have a formula for what A has to be. Yeah, A has to be equal to 1 over this number, AD minus BC, times the matrix D, -C, -B. Sorry, I got that backwards. -B, -C, A. Okay. Right, so then if as well, if AD minus BC is equal to 0, then A is not invertible. So we've got a perfect numerical way of determining whether or not a 2x2 matrix is invertible. And could we call this number AD minus BC the determinant, because it determines things. Determinant of A. Okay. Good. So then, yeah, let's find an inverse for this matrix 1, 2, 3, 4, provided it exists. So the first thing we can do is compute the determinant of A. Here's our solution. And we know that if the determinant is non-zero, then it is invertible, and we can use that previous theorem to find the inverse. So the determinant of A is just going to be 1 times 4 minus 2 times 3, which is 4 minus 6 is -2, which is non-zero. So this means that A inverse is just 1 over -2. And then what are we doing? We want to swap the diagonal ones and negate the off diagonals. So this becomes 4 and 1, and then -2 and -3. Or if you like, you can write this as 4 over -2 is -2, -2 over -2 is 1, -3 over -2 is 3 halves, and then 1 over -2 is -1/2. And then I'll leave it to you to check that if we hit our original matrix, 1, 2, 3, 4, with this alleged inverse, then in fact we do get what's promised, which is 1, 0, 0. Well, let's do one computation together just to make sure. We'll do the first one. This is saying -2 plus 3 is in fact equal to 1, which I agree with, which I'll sign off completely. Okay, so we checked the first one. I'll leave you to check the other 3. Yeah, good. Okay, next theorem. Okay, so yeah, if A is an invertible n-by-n matrix, then for each vector B in Rn, the equation that we're so interested in, Ax is equal to B, has a unique solution. That solution is just A inverse B. And so where does this come from? Again, you should think of all we're trying to do is recreate the algebra we know and love from high school in this new context. So we should think of like, A times X is equal to B, and you can divide both sides by A if we're talking about real numbers. Here, of course, we can't divide by matrices, but we can multiply by their inverse. And that's sort of what's happened here. It looks like we hit both sides with the inverse. When these canceled, and we solve for X. So we're just trying to recreate all of the algebra we know and love with real numbers in the context of matrices. And that's really what the proof sketch is going to be like too, I think. Where's this theorem at? Here we go, yeah. The proof sketch really is, if we assume Ax is equal to B, this means A inverse Ax is equal to A inverse B. But we know that we can bracket this to multiply A and A inverse together first. So this is just the identity matrix times X is A inverse B. But we know that the identity matrix leaves every vector alone, so this is just X is equal to A inverse B. So this shows that if there's a solution, then it has to be X. Yeah. Okay, and there's more details as always in the textbook. Okay, so let's do an example to solve this linear system using matrix inverses. Okay, so then the first thing we should do is translate this into a matrix equation, find the inverse of the matrix, and then apply it to 3, 6, you'll see. So we want Ax is equal to B. So our A should be what? It should be the coefficient matrix. So that's just 1, 2, 4, 5. Oops. 1, 2, 4, 5. 1, 2, 4, 5. Our vector X is just X1 and X2. And B is 3, 6. 1, 2, 4, 5, 3, 6. Great. So if we want to solve this equation, the previous theorem says, okay, you can find solutions for X just by computing the inverse of A and hitting that with B. So let's make sure that A is invertible and then compute the inverse and multiply with B to get it. Okay, so the determinant of A is 1 times 5 minus 2 times 4. That's 5 minus 8 is -3. That's non-zero. So we're happy about that. So then A inverse is just going to be 1 over that determinant times, and we swap the diagonal entries and we negate the off diagonal entries. And that's our inverse. And I'm not gonna multiply that 1/3 in because it's not gonna make my life any easier to do that. So I'm gonna let that 1/3, that negative 1/3 hang out. And so our claim is, this was what, theorem 2.5? Yeah. So theorem 2.5 says x, our solution, is equal to A inverse B, which is 1 over -3, 5, -2, -4, 1, applied to B, which was 3, 6. Okay, and already I can see why this is going to make my life, why I'm happy I left that 1/3 out. It doesn't matter if we apply the 1/3 before or after this matrix multiplication. So we could hit that 1/3 directly onto our vector first and make life easier for us. So this is just going to be 5, -4, -2, 1, and now 3 over -3 is -1, 6 over oh, sorry, I realized I've done something different in my notes. Okay, let's just do it. Let's just do it the straightforward way and multiply these two together first. So 5 times 3 is 15. 15 minus 12 is 3. -4 times 3 is 12, plus 6 is -6. So that's giving us this product. Oh yeah, now this scalar multiplication is easy. This becomes -1 over 3 times 3 is -1. -1 over 3 times -6 is 2. So there's our solution. So x1 is equal to -1, x2 is equal to 2, solves our linear system. Okay, and maybe you were perfectly happy with row reducing an augmented matrix to find the solution. This has some benefits too, though. Okay. Let's look at some properties of inverses. Okay, so let's let A and B be invertible n by n matrices. The first conclusion we can draw is an A inverse is also invertible, and unsurprisingly, the inverse of the inverse matrix is in fact A itself. So this is saying that, among other things, is saying that the inverse of an invertible matrix is also invertible. Here we've got that AB inverse is equal to B inverse times A inverse. So the product of invertible matrices is also invertible, and it's just the product of the inverses in reverse order. And again, you might wonder why this is the case. We'll do a quick sketch of why B actually makes sense. Part C just says that the inverse of the transpose of A is equal to the transpose of the inverse. So those two behave well together. You can do them in whichever order you like, and you're going to be okay. The reason I wanted to talk about the proof, a quick sketch of B, is because, again, looks like there's something funny happening with why should the order change like that? But it makes perfect sense. I claim it makes perfect sense. So notice what? If we multiply AB by B inverse A inverse, oops. We know it's supposed to happen if these two are invertible, or these two are inverse to each other. What ought to happen is that we get back the identity matrix. Okay. And it does, right? We can re-parenthesize this, so it's A, B, B inverse, A inverse. And now this is A times I, A inverse. And now I times any matrix is itself again, so it's A inverse. Okay. So that checks out. So the fact that we've reversed the order is so that we get the correct cancellation for this thing to play out the way we want it to. Notice if we had A, B, A inverse, B inverse, there's no way of canceling anything. Just a bad time. So definitely we want the order to swap when we take the inverse of a product like this. Okay. I think we've got yet another theorem. All right. So we have, that's right, we have this nice criteria for inverse of a 2x2 matrix. And right now we've got no tools for the general n by n case. So the next thing we're going to do is find the necessarily more complicated or involved process for inverting an n by n matrix. Okay. An n by n matrix is invertible if and only if it is row equivalent to the identity matrix. So that's a good criterion. And better still, or at least a more, yeah, in this case, any sequence of elementary row operations used to reduce A to the identity matrix, if we use those same row operations, it'll reduce the identity matrix to A inverse. And so our strategy is going to be make one big matrix with A and the identity matrix on it, reduce A, and it'll produce A inverse on the other side. So let's see what I'm talking about. Let's take this matrix A and show, we're going to show that it is in fact invertible by using this theorem we just saw. So we'll row reduce our solution here. We'll row reduce this giant matrix where it's half of it is A and half of it is the identity matrix. And this is going to help us keep track of the row operations we've done each time. Okay. Right. This theorem is telling us what we want to do is every row operation we use to reduce A to the identity matrix, we also want to apply to the identity matrix because that'll reduce it to A inverse. Okay, and now we're in familiar territory. We're just focusing on making the matrix A here on this left-hand side into the identity matrix if possible. So let's do what? Let's do row 2 plus row 1. We'll do row 3 minus 2 row 1. Okay, so that's 1, 0, 1, 1, 0, 0. This is 0, 2, 4. And then what have we done here? 1, 1, 0. And now we've got 0, 1, 5 minus 2 is 3. And now we want minus 2, 0, 1. Okay, I'm not going to keep on writing this like dotted line to separate these two things, but you could mentally put that there if you like. Okay, so we've made some progress. Next, let's sort of do the obvious thing and just scale row 2 by a half. Oop. So 1, 0, 1, 1, 0, 0, 0, 1, 2. Okay. We have to introduce fractions in that right-hand side. I'm sorry, everybody hates fractions. That's just life, though. I'm not actually sorry. That's life. You're an adult. You can suffer the slings and arrows like anybody else. All right, so let's do row 3 minus row 2. I've not left myself enough room here. All right. Okay, that first row still hasn't really gone anywhere. Neither will the second here. And now what? 0, 0, 1. Row 3 minus row 2. Okay, but negative 2 minus a half is negative 5 halves. But 0 minus a half is minus a half. And then 1 minus 0 is still 1. Okay, we're almost there. Let's do, the last two steps. So we want row 1 minus row 3 and row 2 minus 2 row 3. So 1, 0, 0. Now this is the annoying part. We want 1 minus 5 halves is, 1 minus negative 5 halves is 7 halves. We want 0 minus negative 1 half is 1 half. And then 0 minus 1 is negative 1. Okay, 0, 1, 0. And now what are we doing here? We want 1 half minus 5. I've written this down, but it's illegible. So I'll have to do this by pure thought. Row 2 minus twice row 3. So 1 half minus 5. 5 is 10 halves. So it should be negative 9 halves. That could be what I wrote down. And then we've got what? 1/2 minus 1 is negative 1/2. 1/2 minus 1. I've got 3 halves written down. 1/2 minus negative 1. Okay, it's 3 halves. And we've got, 0 minus negative 2 is minus 2. Okay, and now we're all set. Boom, boom, boom. Very humbling to have to do arithmetic in your head. Yeah. Okay, anyways, so what we've done is we've put these two matrices together. We had A over here, we had the identity matrix here. We've reduced A to the identity matrix, and what happened over here is the inverse of A. So this is now the claim of this theorem. Claim of that above theorem is this matrix is A inverse. Okay, so a concrete way of computing inverse matrices of any size, not just 2 by 2. Okay, that was long and embarrassing. I'll see you all next time with section 2.3. Take care, everybody.